Today for day 6 we're going to take a look at some applications of what we've been working on. So the first thing, find the sum of the series. Well, I notice this is arithmetic and it's going up by 7. So that formula, our sum of an arithmetic of n over 2 times your first term times your last term. Well, I notice here I can fill in 15 and 176, but what about how many terms there are? So we have to figure that out. So we can use the formula for an arithmetic, our first term plus n minus 1 times our difference. So we know our term is 176, 15 plus n minus 1 times our difference of 7. So 176 equals 15 plus 7n minus 7, 8 plus 7n, 176. So we have 168 equals 8n divided by 8. So that would be 21. So we know there's 21 terms over 2. And then we could type this into our calculator and see what we get. So we have 21 over 2 times, and let's see, what did we have here? 15 plus 176. So we have a grand total of, let's see, 2005.5. So the next thing we're going to take a look at here is a formula we looked at last year, compounding interest. A is the amount in our account. This is our principal, the amount we're investing. R is our rate. N is the number of times we're compounding. Now hopefully you remember this from last semester, and T is the time, or usually we see it in years there. So the first problem we're going to look at here, a person deposits $1,000 into account and pays interest 4% compounded quarterly. Assuming no additional withdrawals or deposits, how much will be in the account after 10 years? So our amount, we start with 10,000, 1 plus our rate of 0.04, divided by quarterly 4, so to the power of 4 times 10. So we can type that in 1,000 times 1 plus 0.04 divided by 4 to the power of 4 times 10. And we end up with $1,488.86. So again, I'm hoping that's pretty familiar there. So what we have to watch is just checking here. Let's take a look at this one. The population of a town increases 2% per year. If the predicted population at the start of 1980 was 1250, what is the predicted population at the start of 1220? So it's 2% per year, so we're not compounding. So we start at 12,500, 1 plus just 2%. And how many years is that? That's 40. So let's see what we end up with. 12500 times 1.02 to the power of, oops, forgot the 2, to the power of 40. 27600. And we can't have half a person, so 27601. So let's ask another question on this one. Let's ask, when will it reach? Let's say we want to know 30,000 people. So we want to know when our total is 30,000. And so we could put times 1.02 to the t. So we want to figure out that t. So we can divide by 12,500. So we have 30,000 divided by, so we have 2.4. So when does 2.4 equal 1.02 to the t? Well, this is one where you might remember switching into log form from last semester, so we could rewrite this as a log base 1.02 of 2.4 equals t. And that log key on your calculator right here. So log base, I already forgot what I had, 1.02 of 2.4, and we get 44.2 years. And that makes sense if we're here at 40. So another one, let's say you want the population to equal 50,000. So you want to know when 50,000 equals that. So we divide by 12,500. So we end up with 50,000 divided by 12,500. So we have 4 equals 1.02 to the t. So again, we'll write it in log form, and we remembered our base is the same as the base of our exponent, so 0.02 of 4, that should be an equals t. So we have log 1.02 of 4, and we end up with 70 years. And then we're going to take a look at one more that I want to show you how to use your calculator. Let's say you have an arithmetic sequence, and it starts at 28, and you're adding 50, and you have a geometric that starts at 1. Oops. And you're put that over there, and multiplying by 1.5. You want to know when is the geo, what's the first value, I should say, when the geo is bigger than the arithmetic. So let's see, so we have 28, we're adding 50, so n minus 1 times 50. And we want to know when that is, the geo is bigger. So when does our geo, which starts at 1 times 1.5 to the n minus 1, when is it bigger? Well, this is totally one we can use our calculator for. So if we go back to our graph, we can graph our geo, 28 plus 50 plus n minus 1, because we can get to a table from here. So there's arithmetic, and that makes sense because you know it's going to be linear there. So another one, oops, tab brings up a new one, and we had 1 times 1.5 to the power of x minus 1. Well, we want to know where it's bigger. Well, it looks like, you know, when x is 2, so if we were to interpret this graph here, you know, when x is 2, this one's here, but this arithmetic is way up there because it's shooting way up there. When x is 3, it's here. This x on our line is going to be way up there. So it might be easier, we can't figure it out from the graph, but we can definitely go to our table here. So let's see. So if we go to our table, Control T, so we have our first and our second, and let's see, so 28 and 1, so we want to know when that geometric first becomes bigger. Let's see. Oh, right there. 985 is bigger than 878, so when n is 18. So 18 would be our answer.